In this video, we are trying to explain what are those dynamics, those complex patterns we described in the first video. When we talk about agent-based modeling, we say the first step is to code up individuals' behavior rules, and the second step is to let the model itself to simulate complex dynamic systems, complex patterns. So what are those patterns? Why we say it's complex? So to understand the complex, we can understand this in three ways. First, the reason why we say it's complex is the system as a whole, the ants, say 100 ants as a whole, as a colony, its effects, its behavior, or its ability will be greater than single ant's ability multiply, say 100 or 200. So if the whole is greater than the sum of individuals, we say this effect, this pattern is a complex pattern. This is one way of understanding it. Second way of understanding it is that if based on single ant's behavior, and we trying to imagine how many ants as a whole would behave if those kind of imagination or those kind of phenomena we generated in our mind is not quite compatible to the real world ant colony behavior, now we say that kind of behavior is not easily foreseeable. So we say that kind of behavior is complex. For example, about the food, the ants trying to get food. If the food has the same different distance to the nest and the food pile have the same amount of food, then our imagination would be the nest will send out equal amount of ants towards this two pile of food and trying to get the two piles of food at the same time. So the two piles of food will be transported back to the nest at the same time. That is how we intuitively predict what would happen. But in reality, as biologists observed and told us that even for the same distance and amounts of two piles of food, the ants will devote most of their resources to get one pile of food first and then move on to the second pile of food. So this real world phenomenon is different from how we intuitively predict. So if this kind of thing happens, we say this kind of phenomenon is complex. And the third way of understanding it is that if the phenomenon we observe from the world, or we trying to code that kind of phenomenon up, we realize that those kind of coding task is too difficult, too massive to perceive, to understand, to write it up. And if that happens, we say this kind of phenomenon or pattern is complex. So let's look at a few examples. For the first understanding that the whole is greater than the sum of individuals, we can use ants model as example. Say we have an ant colony with 100 ants, and we use the food gathering ability as a measure to the ability of ant colony, and also as the ability to assess any single ant's food gathering ability. So if a single ant's food gathering ability, say, is 3.7, then 100 ants added together, that ability should be sum up to 370. However, the same amount of ants as a whole, as a colony, as a system as a whole, its food gathering ability should be greater than 370. It may be 400 or 450 food gathering ability. So the whole is greater than the sum of individuals. This is corresponding to the first definition or first understanding of complex pattern. And the second example is correspond to the second understanding, which is see whether the real world phenomenon is compatible with our assumption of a naive prediction. For this two pile of food with equal distance and equal amounts, can our model simulate the behavior of ant colony that the ants as a whole were trying to get one pile of food first and then to the other equal distance, equal amount of pile of food? If that happens, it indicates that our model is producing some real complex phenomenon. Let's have a look of the model itself. So we set the population to be 130. We set the chemical diffusion rate at 60 and its evaporation rate at 7. And let's run it. It seems that with two equal distance, equal amount of food, it gets one pile of food first and then the other pile. But this time, it seems they get it altogether the same. Okay, try again. Okay, this part's finished first. Okay. One last experiment. Let's say we get 200 ants. See any difference? Okay, so far it seems that our model for the two equal distance and equal amount of food piles, it will prioritize one pile of food first and then the other most of the time.